Okay, so welcome back again. This is going to be part number 5 and episode number 24. And this is the chapter again, groups, context, communicators, and caching in MPI. So we're going to continue from where we left off. We basically explained the semantics and the behavior of this example, MPI comes split inter, but we haven't seen the code. And here I want to basically show you the code. We have 9 processes. The reason for that is because we have 5 processes here on the left and 4 processes on the right. And then we split that to have the original intercommunicator that we wanted. Notice that we put an equal sign here because 9 divided by 2 is going to be 4 something. So we want all the processes from 0 to 4, 0, 1, 2, 3, and 4 in left group. That is why we put a plus sign here. And another reason that we put here a +1 is because that the remote leader is going to be, so processes 0 through 4 is going to be in group A. Process number 5 is going to be the remote leader of group A, right? So that is why 9 divided by 2 is going to be 4 point something. Since this is an integer division, it's going to be 4. Plus 1 is going to make it 5. So all processes in group A are going to pass in 5, and all processes in group B are going to pass in 0, which is the remote leader of group A. Okay. So, and then we have this intercom create, that's the call. But what is super important is that, so this is where we basically created that intercommunicator. So this is our original intercommunicator. So up to this line, we basically created group A, group B, with 5 processes on the left, 4 processes on the right. Now we want to see how we can create these 3 sub-intercommunicators. So 3 sub-intercommunicators, that's so funny. So we say new intercommunicator with MPI comes split operation. So we need a new color and we need a key. And for group A, so with all processes here on the left-hand side, because I didn't see any sort of pattern, how they put it into color 0, color 1, and color 2. So that is why I put a switch statement here. So I switched with a local rank. So if it's 0, then basically I go through all the processes from 0 to 4. Let's take a look at 1 or 2, and then we know how it works. So if your local rank is equals to 0 in group A, so this means that we are at this process. So color is 0, and then the key is 1. Color is 0, key is 1. It's exactly the same. So this is process 1. Take a look at it. Color is 0, key is 0. Color 0, key 0. All the way to process 4, we do the same thing. In processes in group B, that's the else statement. We switch again the local rank. Process 0 is going to be color 0 and key 0. Color 0, key 0. All the way up to process 3 here. So you get the logic, right? So you need to basically have a color and a key so that you can basically subdivide your original intercommunicator. We have allocated a color and a key. Now it's time to basically create our new intercommunicator and then use this MPI come split. What is the original communicator? It's the intercom. That's the original intercommunicator we created with that splitting operation. What is the color that you want to have? It's the new color strategy or scheme. What is the key you want to have? It's the key that we allocated already in those if statements. And then we pass in our new intercommunicator. And you see that now we have 3 disjoint output communicators. And then you can ask for rank, for size, and then ask for each one of those processes to check their rank and check their size. Okay, if new color is 0, so this means that we are in the first category. So group A and group B are associated to first category. So group A is going to have 2 elements, or 2 processes. Group B is going to have 2 processes. If color is 1, so this means that we are in the next sort of sub intercommunicator. We're going to have group A 1 element, group B 1 element. So that is new intercommunicator 2. So I put these sort of colors into this intercommunicator 1, intercommunicator 2, and this is intercommunicator 3. And within each of those, you see that new color is 1. Within each of those, the color 0 shows the corresponding group A, and the color 1 basically shows the corresponding group B. And this is, when I say corresponding group A, it means that the corresponding group A, which is a subgroup of the original group A, which is this one. So for example, with this 5 processes, the corresponding group A is only processes 0 and 1, which is a subgroup of this sort of original group A. So that is what it means. And then we need to do some freeing with those new intercommunicator, the original intercommunicator, and local intercommunicator. This example is very, very beautiful. Let's take a look at it. Split, inter, and then I'm gonna run it. How many processes it was? I think it was 9, right? So we're gonna put 9 here. So now you see that new intercommunicator 1, new intercommunicator 1, new intercommunicator 1, new intercommunicator 1. So this is group A. You see that local rank is the rank that they have here. So 0 and 1. But what is important for us is the local rank. So you see that group A has process 0, group A has process 1. So that is process 0, that is process 1. Take a look at group B in the first category. These are group B in first category. Process 3 and process 0. Process 3 and process 0. So I think local rank is probably the most important thing which we can distinguish. But I also provided the world rank that they have, and local rank. It's probably a little bit confusing, but local rank is the rank that they have inside that disjoint sub intercommunicator. Let's take a look at the next category. This is going to be category 2. So let's take a look at it. This is category 2. So we have process 4 in group A. We have process 4 in group A. In group B, we have process 1. That is process 1. Let's go to the next one. That is new intercommunicator 3. This is group B, but we start with group A. So this is group A. So you see that in group A, I have rank 2. So I have a process 2. I should have also process 3. If not, it's a mistake. So let's take a look. Where is it? Oh, here. It's actually the next line. So I have processes 2 and 3 in group A, 2 and 3 in group A, and I have here, which is a group B, and I have process 2 here. You see that everything basically beautifully matches. So this visualization in MPI standard reflects itself into this beautiful code example that you can follow. Okay. We're going to continue. These are the examples we don't care about. Okay, a summary. MPI come create can take an intercommunicator, can take an intra-communicator. MPI come create group can only take intra-communicator. And MPI come split can take intercommunicator and intra-communicator. So these are the things that we have covered so far. MPI come split type. So these are sort of cousins of MPI come split, but you remember in MPI come split, we had a color function, but here we have a split type. So this is like categories of a splitting mechanisms, let's say, or a splitting mechanics. So here again, you take your, let's say, pre-existing communicator, you take the splitting type, its type of processes to be grouped together. Then you get again a key which controls the ranking or the ordering of those processes. You take an info handle, you see that it's an in-out sort of handle, and then you take also as an output your new intercommunicator. This is how it looks like the C binding. You see that MPI com, MPI. So the split type is actually an integer. The key is also an integer. The info is MPI info, and the communicator is sort of a pointer. So this function partitions groups associated with com into disjoint subgroups such that each subgroup contains all MPI processes in the same grouping referred by split type. Within each subgroup, the MPI processes are ranked in the order defined by the value of the argument key, with ties broken according to the rank in the old group. So these are all the same explanations as we had in MPI com split. But here's the difference. All MPI processes in the group associated with com must provide the same split type, but each MPI no, this is actually the same, also similar to MPI com split. But the difference comes from the fact that for a splitting mechanism, we were using a color function or a color scheme to split our communicators into subcommunicators. But here we use a split type, which these are sort of these following values are defined by MPI. So as a split type, you can choose one of these options that we are gonna basically see. I'm not going to spend too much time here, and I have a very simple example here because I'm using my laptop only here. So probably the best and the easiest option is this MPI type shared, because you see that those my processes have a shared memory domain, or they can create a shared memory segment. So but in a proper setup, if you have, for example, if you're working with a cluster, you can try actually other options as well to see that whether you can successfully try to create subcommunicators based on these criterias that we're going to see one by one, but we're not going to spend too much time on this. So the first option you can provide as a splitting type, so this is something similar to the coloring scheme, is the value of MPI com, basically shows the communicator type shared. That's all. This means that all MPI processes in the group of new communicator are part of the same shared memory domain. So that's what I said, that when I'm using my laptop, then this is probably the easiest option that I can go with. And can create a shared memory segment, for example, with a successful call to MPI win allocate shared. So this segment can subsequently be used for load and store accesses by all MPI processes in new communicator. Okay, that's the first one. The second one on the line is MPI com type hardware guided or HW guided. That's hardware guided. This value specifies that the communicator com is split according to a hardware resource type. For example, can be a computing core, it can be a level 3 cache, or it can be, for example, I don't know, a NUMA node or things of that nature. So specified by the MPI hardware resource type info key. You remember that we had an info key here as well. Boom. So each output communicator newcom corresponds to a single instance of the specified hardware resource type. The MPI processes in the group associated with the output communicator newcom utilize that specific hardware resource type instance and no other instance of the same hardware resource type. If an MPI process doesn't meet the above criteria, then MPI com null is going to get returned. But MPI com null is also going to get returned in the following cases. If you pass in MPI info null, then you're going to get MPI com null. If the info handle doesn't include the key MPI hardware resource type, which is important for this hardware guided, then you're going to get MPI com null. If the MPI implementation, which we have impeach in this case, neither recognizes nor supports the info key MPI hardware resource type, then you're going to get that MPI com null. Or if it supports that, supports the info key, but it doesn't recognize what you put in there as the value for that key. For example, we said that it can be a computing core, it can be a level 3 cache, or stuff of that nature. Okay. So the MPI implementation will return in the group of the output communicator and new communicator the largest subset of MPI processes that match the splitting criterion. Yeah, we can actually skip these parts. The next one on the line is maybe let's take a look at this rationale, because MPI, you can also pass in this info key, the MPI shared memory. This is also in consistency with MPI type shared. So you can also basically select hardware guided, but with MPI shared memory, which is going to have the same effect as MPI type shared. So you can see this rationale that the value of MPI shared memory is defined in order to ensure consistency between the use of MPI type shared and the use of MPI type hardware guided. All MPI processes must provide the same value for the info key MPI hardware resource type. This is also super important. And you see a very simple example how you can split the MPI world into NUMA node subcommunicators. And you see that you have a hardware communicator, you have the info handle, you have the rank, and then what you do is that you basically pass in, you set that info handle with MPI hardware resource type, you pass in the NUMA node, that's your basically criterion of the hardware that you want to break down your communicator into subcommunicators based on that hardware resource. And then you call this MPI split type. You pass in your original communicator, which is the MPI world, and then you pass in MPI type hardware guided, and you pass in the rank, the info, which has this basically key and the value, and then you pass in the original communicator. Okay, and this original communicator is basically the communicator of MPI world. This is how you wanted to break down your original communicator into subcommunicators. MPI type resource guided is similar to hardware guided, but this value specifies that the communicator is split according to a hardware resource type, for example, a computing core or a level 3 cache or a NUMA node with this MPI hardware resource type info key, or to a logical resource type. That's the difference between hardware guided and resource guided. With this logical call, you can see a process set name. We haven't seen this one. This is the session model, so we're not going to comment on that. So this is a different sort of key that you can pass in with the info handle, MPI set name, the process set name. Again, you're going to get MPI null if an MPI process doesn't meet the criteria above. It's going to get MPI null, or in these scenarios that if MPI info null is provided, or if the handle is not known, MPI hardware resource type is not supported, I don't know, or the implementation doesn't recognize what you support as the value for those keys. I don't know. Like all these other scenarios, it's going to return MPI null. I have skipped it. I'll put an X on that. Use of more than one info key is erroneous. So when you want to use info keys, you need to make sure that you are using only one sort of criteria, let's say. Okay, so these are like examples, like MPI hardware resource type. You can pass it as NUMA node or package, which is a collection of cores, or level 3 cache, or stuff like that. Or MPI shared memory is, again, to have consistency between MPI type shared and MPI type resource guided. So you can read the rest of them. As I said, since we haven't talked about the session model, and we are not having sort of a cluster, access to a cluster, so that we can show all these different hardware guided ways to break down your original communicator into some subcommunicators. That is why we don't go into depth with these things. Actually, I do have an example, which, as I said, I used only that. It's MPI split type. So MPI split type. So I only used this MPI type shared, which basically all the processes who have access to the shared memory domain, they're going to be grouped into one subcommunicator. In my case, it's going to be all my processes are going to be basically again grouped into a subcommunicator. It might be dubious in this case, but this is an example which shows that how you can use the syntax, at least with MPI split type. You pass in your original communicator, that's the intra-communicator that we have. Then you pass in the criteria for splitting, and then you pass in the rank as the key for let's say ordering of your processes. And then here I passed in an info null, and I passed in my new, let's say, what's it called? It's the new subcommunicator that I wanted to generate. And if the value returned here is not an MPI null, then I can ask for the rank and the size of that communicator or subcommunicator. And then all those valid processes they are responsible to free that resource or that communicator, hardware communicator. So I can say MPI CC MPI split type, and I can run it. You see that I use 9 processes, and you see that since it's on a shared memory, all of those processes again in MPI world are basically reflected into hardware communicator. That's the communicator. That's the subcommunicator that I wanted to have. But in this case, the subcommunicator is exactly equal to the original inter-communicator MPI world. And you see the size is 9. But one thing which is interesting is that there was a visualization here with the next thing on the line. A very beautiful visualization. So we have MPI type hardware unguided. The group of the MPI processes associated with new communicator must be a strict subset of the group associated with communicator, and each new communicator corresponds to a single instance of a hardware resource type. For example, it can be a computing core, it can be a level 3 cache, or a NUMA node, or stuff of that nature. All MPI processes in the group associated with communicator that utilize that specific hardware resource type instance and no other instance of the same hardware resource type are included in the group of new communicator. Okay, so now you can use this sort of type hardware unguided to sort of recursively try to basically break down your communicator into subcommunicators, and then break that communicators into more subcommunicators, and then break those subcommunicators into more subcommunicators. So you can have, you see, if the hardware resources are hierarchically organized, calling this routine several times using as its inputs communicator the output communicator new in the previous call, then it can create a sequence of new communicators in each MPI process, which exposes a hierarchical view of the hardware platform, as shown in example 7.5. That is very, very beautiful. It basically shows, this is example 7.5, but the figure 7.3. So that's the figure. It's the recursive splitting of MPI world with MPI split type. And the splitting type that we pass in here is MPI type hardware unguided. These dashed lines showing the communicators, and the solid lines are basically showing the hardware resources that we have. So here, for example, we have 2 racks, rack 0 and rack 1. You see that our MPI world communicator is basically the whole rack 0 up until NUMA node 0 in rack 1. And then we do one splitting. This is the first level of splitting. We end up with this green lights or green dash lines. So it's going to be rack wise. So rack 0, that's one sort of subcommunicator. The second subcommunicator is going to be the NUMA node 0 of rack 1. And then another level of splitting is going to end up, for the upper portion, is going to end up into NUMA node 0. And NUMA node 1, whoops, it's 25 minutes, it's also over. I'm going to finish this and then continue in the next sort of episode. So another level of splitting is going to end up in these sort of light red ones, NUMA node 0, NUMA node 1. And for the bottom half is going to end up with CPU 0 in NUMA node 0 and CPU 1 in NUMA node 0 of rack 1. And then again, splitting that further, it's going to end up with these sort of dark red as my eye see. So in the upper portion, it's going to end up with CPU 0, CPU 1, CPU 2, and CPU 3. And in the bottom portion, it's going to end up with core 0, core 1, processes 8, 9, 10, 11. And you see that, for example, here, proc 6 and 7, for example, return MPI com null. So we don't have further splitting here in the CPU 3. And then processes 8 to 11. So these are these 8, 9, 10, and 11. We don't have any further splitting here as well. And for the processes 0 to 5, 0, 1, 2, 3, 4, 5, you can split even further. The next level of a splitting, which happens here, split number 4, is going to end up going into these green sort of domains, which gives you the core 0, core 1, and core 2, core 3, core 4, and core 5. So this basically, so now you can basically understand when we, in MPI, when we say process, so in hardware world, it can basically reflect any of these. It can reflect the rack, it can reflect the NUMA node, it can reflect the CPU, it can reflect individual cores even. So yeah. And then yeah, I think that's basically what you need to know. I don't want to spend too much time on this because, as I said, we don't have necessary ingredients for that. But you can read the rest if you're interested more. I'm going to stop here basically because we had our 25 minutes.